Hey, Physics students, this is Mr. Evely speaking to you. This is a follow-up video on some of the things we're doing in magnetic fields. Already we've taken a look at the definition of a magnetic field, which is really based not on what the field does to a particular magnetic particle, but what it does to a charged particle when it's got a velocity in a magnetic field. We saw that the force is equal to the charge times the velocity crossed with the field. So it's a cross product and math that you've done before. Now it's an interesting application of that math, but it's kind of bizarre to think that when you're talking about gravitational fields, that gravitational fields act on mass. When we talk about electrical fields act on charge. Talk about magnetic fields act on charges that are moving. So you see that very clear connection between electrical fields and magnetic fields. Now, hopefully, you have read in the textbook sections 4 and 5 dealing with crossed fields, that a charge moving through a magnetic field can experience a force in one direction, and that force can be balanced out by an electric field. So we can have perpendicular magnetic and electric fields that balance out the forces on a charge and allow it to move freely through that space. And what it did is it allowed us to do a couple of things. It allowed us to measure the properties of electrons, but also creates something called the Hall effect, which is kind of an interesting effect in physics and has a lot of application in the measurement of magnetic fields. My topic for today, however, is this idea of charges moving in a magnetic field in a circular path. So what I'd like to do is take you through that. We're going to call this Roman numeral 2. Don't get too hung up on the Roman numerals, but we call this part 2. And this is the centripetal force on a charged particle confined to an xy plane. So imagine that this is x and y. And imagine also that we have a magnetic field that goes into the page. So imagine the little magnetic field arrows are pointing away from us. I always imagine that the x's are the fletchings of the arrow, the feathers on the arrow that are pointing away from us. If you imagine little arrows going into the page. Okay. Now imagine a positive charge moving through this magnetic field in this direction. Okay, so there's its velocity. At that moment, as it moves through the field, we imagine that there is a force on this thing. And again, we do a QV cross B. We would notice that, all right, the direction of the velocity vector is in the direction of my fingers. The direction of the magnetic field is into the page. Therefore, with my right hand, we realize that there's a force on the particle toward the left. So there's a force this way. Now, what that's going to do, as long as this velocity is perpendicular to the field going into the page, is it's not going to change the kinetic energy of this particle because the force is perpendicular to the direction of the particle. What it will do is change the direction of that velocity. So the object will, the charged object will begin to curve. And notice that when it begins to curve, the velocity direction changes, but it remains perpendicular to the field. And so the force is still perpendicular to the velocity at all times. Okay, what you'll end up with is a nice curve. As the particle comes around, the force always points toward the center. The velocity is always tangent to the curve. And so you'll get a nice circular pattern. Now, of course, when something moves in a circular path, we invoke good old F equals ma, where A sub c stands for the centripetal acceleration. So that force that we've created is m times v squared over r. Super basic physics. However, the force arises due to the magnetic field. And we know what that is. That's QV cross B. Now I'm going to leave the cross of this out because the magnetic field is already perpendicular to the velocity and remains perpendicular to the velocity. Therefore, we've got sine of 90 degrees going on here. So we'll say, look, QVB equals mv squared over r. Okay. Now, if we rearrange this slightly, well, first thing we notice is we can lose one of our velocities, and we end up with Q times B equals mv over r. Okay. And rearranging slightly, we note that the radius of curvature of this thing is mv over qb. So that's a nice result. Radius of the object as it moves through the magnetic field. Note its mass is important. So if, say, this is a proton, that would be the proton's mass, its velocity, its charge, and the strength of the field. Now, we also know that the velocity of an object as it moves around in a circle, remember, is displacement over time, but this thing moves in a circle. The distance it moves during a certain period of time is 2 pi r divided by t, where t is the period. In other words, that's the time it takes this thing to move around one circle. Replacing the velocity with this value, we get r equals m times 2 pi r over qtb. Lose our r's here and rearrange, we get the period equals 2 pi m over q times b. Okay, remembering that the period is just 1 over the frequency, or the frequency is 1 over the period. Frequency is, of course, qb over 2 pi m. All right, and you may remember also that we can express this in terms of omega. So moving this up just a little bit. Remember that omega is 2 pi radians divided by the period, or 2 pi times the frequency. So we can also say that the angular velocity of this little booger would be equal to qb over m. So just kind of a nicer, cleaner way of stating the same thing. All right. Now what's interesting is that if v and b are not perpendicular to each other, that v has some angle other than 90 degrees to the magnetic field, that the particle will take on a spiral path. The perpendicular component can be used as a way of finding the centripetal force, the period, the frequency, or the angular velocity. But the parallel component will determine the speed at which the spiral progresses. So it's kind of hard to imagine what this looks like, but imagine that the B field is going in this direction. Okay, and the velocity vector is in this direction. Now that velocity vector has two components to it. So imagine this angle phi is the angle between the actual velocity and the magnetic field. This, it would be the perpendicular component. So imagine that as it goes this way, it'll curve, say, into the page. Let's check this out. Okay, using the right-hand rule, we put our fingers in the direction of the velocity. We put our curl our fingers into the direction of B, and the force, the magnetic force, is into the page. So you can imagine 3D that this particle is going to circle out of the page and into the page, a circle that has its plane perpendicular to the page, but it's still got this component this way. So as it circles, okay, trying to draw this 3D, as it circles, it will also continue to move in this direction at a particular speed. Okay? So this is kind of weird stuff, but what this is representing is the helical path of a charged particle in a magnetic field. Okay? Now this is a more general case where the velocity is not exactly perpendicular to the field. So again, here's our B field, here's the velocity, here's V cosine phi, here's V sine of phi. V sine of phi is taking the place of V in our previous equation. This guy here will determine how fast the spiral progresses in this direction. Okay, let's do a couple of examples and see if we can make some sense out of this. Okay, here's my first. And this one doesn't involve the crazy helix. This is just a normal problem where you imagine a proton is in a circular orbit of radius 2 centimeters, perpendicular to a 0.8 Tesla field. Find A, its period, A, its speed, B, its period, C, its kinetic energy. Suppose that our field is coming up out of the page. So again, it's kind of 3D, but I'm going to draw our arrows coming out of the page. So imagine that the points on these arrows are little cones. So if you think of an arrow as having a conical tip, we're looking at the dots representing the tips of the arrows and the circles representing the cross-section of the cone. So imagine this cone is coming right out of the page at you. So this represents the arrow, and you're looking at the tips coming out of the page. Now, send a proton through this field, positively charged little particle, moving this way through the field. Okay, right-hand rule would say, all right, let's move our fingers, point our fingers in the direction of the velocity. The field is out of the page, so I'm going to bend my fingers up toward the camera. The force on the proton is, according to the right-hand rule, to the right. So this guy is experiencing a force in this direction. Now, that force is not going to speed up the particle or slow it down. Think about what you know about work. If we're going to change the kinetic energy of a particle, we have to do work on it. But its displacement is straight up toward the top of the page. The force is perpendicular to that displacement. Therefore, this force is doing no work at all on the particle. It's not changing its energy. It'll only change the velocity, and that is the direction of the velocity, not the magnitude of the velocity. So this particle's path is going to curve around in a circle because no matter where he is, the force is going to be toward the center, perpendicular to the velocity, and that's about the worst circle I've ever drawn in my life. All right, so this circle has radius r. They're telling us that r is equal to 0.200 meters. They're telling us the B field is 0.80 Teslas. The mass of a proton is a given quantity, one of the constants in the universe, 1.67 times 10 to the negative 27 kilograms. The charge on a proton, of course, is the elementary charge, and that is 1.602 times 10 to the negative 19 coulombs. All right, so if I'd like to know how fast this little guy is moving, one way to do it again is to say, all right, the centripetal force causing this thing to move is mv squared over r. The force, however, remember the force is qv cross b, or the magnitude of the force qvb sine theta, where theta is the angle between this velocity and the magnetic field, which of course is 90 degrees, which is 1. So I'm going to claim that this is qvb. We can divide both sides by v, get rid of one of them, and solve this thing for v. V is equal to qbr over m. If we put our numbers in, 1.602 times 10 to the negative 19 coulombs, moving through a magnetic field of 0.80 teslas. The circle has a radius of 0.20 meters, and the mass of a proton, 1.5 times 10, I beg your pardon, 1.67 times 10 to the negative 27. And that's in kilograms. Apologize for that. 1.67 times 10 to the negative 27. Punch it all out, and you get 1.5 times 10 to the 7 meters per second. So this guy would have to be moving at a pretty good speed, a pretty good chunk of the speed of light. Okay, so how do we get the period? Okay, let me grab a sheet of paper to continue here. Remember, the period comes from the velocity. This thing moves one circumference every period. Therefore, the period is equal to 2 pi r over the velocity. And we know all that stuff. So punch in 2 pi times the radius of the orbit divided by this 1.5 times 10 to the 7. I would use the unrounded version when you punch it through, leave it in your calculator from before, and get 8.2 times 10 to the negative 8 seconds. That's part B, by the way. And then part C, sorry about that, kind of left the screen there. Part C is find the kinetic energy. So that's not so bad either. Kinetic energy is 1/2 mv squared. So one way of finding the kinetic energy is to just bulldog approach, put the mass in, put that velocity in that we calculated from before, and have at it. All right, so even though this thing is moving some good fraction of the speed of light, its kinetic energy is really small. Why? Its mass is tiny. It's a little tiny proton. Okay, my next example deals with this three-dimensional helix craziness. All right, so we have an electron moving at 4 times 10 to the 6 meters per second, entering a uniform B field, 0.040 teslas, at an angle of 30 degrees to the field lines. What's the pitch of the helical path? Now, take a look at this video real quick. See if I can make this run. Okay, so here is a magnetic field that represented by the green arrows pointing upward. This is what we're talking about. So as the object moves in a circular path, because it has a little bit of a component of its velocity parallel to those magnetic field lines, it moves slowly upward while it's making these circles. So it's nothing really crazy or super difficult. It's just the fact that it's in 3D kind of drives us nuts at times. All right, so we have this electron moving at 4 times 10 to the 6 meters per second, entering a uniform magnetic field of 0.040 teslas at 30 degrees to the field lines. What's the pitch of the helical path? So imagine we've got our field lines going in this direction. Okay, if we have an electron entering from the other direction, let's say if it were to enter this way, exactly perpendicular to the field lines, what's going to happen is we're going to have a force on that thing according to the right-hand rule, which says, okay, put our fingers in the direction of the velocity of the electron, bend them in the direction of the velocity of the B field, and our fingers, our thumb that is, points in the direction of the force on a positive charge. But an electron is a negative charge, so it's going to behave in the exact opposite way, and there'll be a force into the page. Now again, think three-dimensionally. If there's a force into the page, the electron is going to curve into the page, and there'll be a circle. The circle will actually be in a plane that's perpendicular to the page here. So it'll be going out and back into the page like so. So this circle, from our point of view, will look like a line because he's going in and out of the page. But that's only if the electron's path is exactly perpendicular to the B field lines. This thing is at an angle, and they said that the angle is 30 degrees relative to the magnetic field. So this is 30 degrees. So this guy has a velocity, this electron, little electron dude, has a velocity that is at an angle relative to the field. So this portion of the velocity is going to make sure that it moves in a circular path. This portion of the velocity is going to make sure that circular path moves upward. So it's going to be this spiral that's going to occur and move up the page. Now, the pitch, this thing, is actually the distance between spirals. So one spiral occurs. When the next spiral occurs, how much higher is the electron? And then the next one occurs. And these things are called the pitch. They should be equal, by the way. And as this thing, this electron moves through the field, how far apart are these circles as they occur? So what we're going to do in order to come up with this pitch is we're going to say, okay, the velocity this way is v cosine theta. I'd like to know how far this way the electron moves in the time it takes to make one circle. That will be the pitch. As it makes one circle, it moves upward at this velocity. So if we say velocity is just distance over time, what we're going to do is say this v cosine theta is equal to this pitch number divided by the time it takes to make one circle. So this pitch, this thing we're talking about, is equal to v cosine theta times t. Now we said earlier that t is equal to 2 pi m over qb. So I'm going to rewrite my equation to say that it's going to be v cosine theta times the period 2 pi m over q times b. And we're going to go ahead and put in our numbers. So velocity, 4 times 10 to the 6 meters per second, times the cosine of 30 degrees, times 2 pi, times the mass of an electron, which is like 9.1 times 10 to the negative 31 kilograms, divided by QB. Q, of course, is 1.602 times 10 to the negative 19 coulombs. We've already taken into account the fact that it's negative, but that's okay. And then, of course, the B field is given as 0.040 teslas. The pitch, therefore, is 0.00309 meters, or roughly 31 millimeters. I beg your pardon, 3.1 millimeters. I can't do simple math in my head anymore. There we go. Okay, so this seems a bit odd. It seems a bit strange. Hopefully the video helps. Hopefully it helps to think about it in terms of two different motions. One is circular motion, just, in a plane that is perpendicular to the plane, and the other is just regular old velocity as these circles move up. That turns into a helix. All right, so kind of a strange problem, kind of a weird three-dimensional problem, but in the end, not too terrible. All right, so that concludes what I have for today is particles moving in circular paths in magnetic fields. The next one is dealing with the magnetic forces on wires that carry current, but we're going to save that for another video. Thank you very much, guys. I will talk to you later, and also there'll probably be an assignment over this. This is Dr. Evil out.